get started here in just a sec. Yo, what up? Okay, so the purpose of this is going to be to give an overview of where this project stands because it's nearing completion and kind of the next steps I'm going to be taking in how we're going to try to bridge the gap between this and my other project, and kind of to give an overview of all the kind of concepts and things I had to learn in order to make this work. So here we are in space, and the whole purpose of this project is to be able to represent a universe for a space game. It's to represent everything larger than a solar system, basically. So this is our universe, and we're kind of drifting through it. And the whole idea here is that we can kind of procedurally generate and load in galaxies, and then eventually procedurally generate and load in star systems, and then eventually generate and load in things for the star system. So this is kind of handling all the stuff that's too big to do in world space. So we're using virtual coordinate systems driven by octrees and parallax, and we'll see here in a moment as I get close to this guy. Did I may have, hold on. I know one should be right. Technical difficulties. Let's find another one. Well, something has gone wrong with my sprite material. It's supposed to be fading out before now. I guess we'll have to fix this in real time. Hang on. Yeah, we'll just do this. So this is supposed to handle like basically our transition. There's still a little bit of work to do on it, but for some reason it was failing there, and I was working this yesterday, so I probably janked something up, but let's see if we can get one to load in editor mode, because it was working for me in editor mode. There it is. Okay. Yeah, something about the FOV determination, but you can see here we've got a nice little spiral galaxy that's been generated, and it all works. So I kind of wanted to show like the results before we kind of go over what goes into this. But the first thing that you should understand is that this is all voxel based, so we're using octrees. We have a universe level octree and a galaxy level octree that spawns in when we spawn a galaxy. We populate it with procedural generation techniques for different types of galaxies based on a galactic type chart that I pulled in. So there's different types of spirals it can do. If we cruise around long enough, we'll find globular and clusters that are not spiral, and things like that. So trying to find if we can find some different galaxies by cruising around, and then I'll zoom out and we'll look at the whole universe, because we did like a sort of like a pseudo cosmic web generation function for that. That looks like it's just a globular cluster there. Yeah, so this would be an example of just like a simple globular cluster. I haven't done the black hole yet, so it's just a really bright placeholder that accumulates density and color data from all the stars it absorbs. But eventually we'll do a black hole for the center of these things. The data's there, we just need an asset to represent it in the particle system. We'll probably look at a couple more galaxies here, and then I'm gonna kind of briefly go over the various concepts. I'm not going to go into in depth on anything here, just because there's a lot. But the first thing I just wanted to mention is that all of this is backed by octree data structures, sparse voxel octrees, and we can kind of look at what the payload of that looks like. But basically, we have a gas density field and a density field, a composition vector, and then our octree data structure that we pump all that data into to generate the various procedural bits and pieces of it. So I'm not gonna go over how an octree works, because that could be a whole probably series of videos in and of itself. But what I can show is a quick diagram. What it basically amounts to is breaking down 3D space into cubes, and then further subdividing those cubes as needed until you get to whatever depth you want to place data into your tree at. In our case, we do a density accumulation. Basically, if I insert a point, first it has to traverse through the root node and then through the subsequent nodes until it gets down to the depth and position that we wanted it to live in, the data to live in, right? So let's say we generate a star or something. But each data payload that we're inserting also contains a gas density value. And that gas density value gets accumulated by every parent node that it passes through on its way down to being inserted at whatever depth it's being inserted into. And then at basically after the data is generated, we can then exhaustively sample a layer at like a pretty shallow depth. Like for example, here I'm using a 32 by 32 by 32 sample, which equates to, I believe, depth 6 or 5. I don't remember exactly, but basically after we've inserted all of our stars, they accumulate the gas density into all layers of the octree as they pass through it, and then we can sample different layers of it to get our actual volumetric density data, which is combined with some other techniques to give us kind of the gas appearance of these galaxies, which is varied because it's all hooked up to a proceduralization harness now, and I don't actually have any control over what galaxies are getting generated here. It's all completely randomized. So like when I go to one, I don't know what colors it's going to be, what it's going to look like, things like that. So here we got a nice like 2-arm barred spiral. Looks like a bit of orange and gray in the volumetric here. And then if we speed up our relative velocity, we can kind of look at our cosmic web here. I didn't do anything mega complicated here. It's based off a noise formula from fast noise integration, but I will talk about that a little bit later when I get to the generators. So long story short, we store our data in an octree. The next technique, the next most important thing, would be the concept of parallax motion. This is how we're able to represent these as very large scale structures, but still be able to traverse them and have precision. So what parallax motion is, I think it's probably easier to demonstrate it. So we'll go ahead and spawn a galaxy, and then we can inject and take a look at what that looks like. So we spawn a galaxy here. We'll get close enough to where the sprite disappears and we can see it. We want it to be small, but okay. So we're far away from this galaxy, right? And it looks like it spawned in the location that the parent particle was in the universe scale. But that's not actually the case. So if I eject here and I zoom out, we can see that our universe particle system here and our galaxy particle system is way down here. And what's more, they're about the same size. The galaxy here is actually exactly the same size as our universe here. And that's basically the secret of it. So let's go ahead and hook back in. So now we're controlling it again. And let's go a little bit closer to this galaxy. Alright, now we're fully filling up our viewport with it. And let's go ahead and eject again and see what this looks like now. So the galaxy didn't actually change in size, and we did get closer to it, but when we're in perspective, the galaxy looks like it's right here, but it's actually further away than most of the things in the universe. It's still outside. Now let's go to the very center. So we'll go right here next to the black hole for this galaxy. Once I get close to it. Okay, this is pretty close. So we'll eject one more time and take a look at what this looks like. Now it is completely overlapping our universe. So what is actually going on is that these are moving at different rates of speed, and they're moving at the same time as the player moves. And we're using a parallax function. We have a constant speed value, which can be used to control our quote-unquote like warp speed, traveling faster than solar system level speeds. And that is the same for all of these. But then we have another factor, which is unit scale. And unit scale for the universe or for a galaxy defines, okay, Unreal World units are in 1 centimeter units. So our unit scale that we assign to a galaxy or a universe is what size do we want 1 centimeter to act like. So if, for example, my unit scale was 100,000, then for me to travel 1 centimeter inside let's say our universe is set to 100,000, then for me to travel 1 centimeter in the universe relative to the player's perspective, I would have to travel 1 kilometer. So you travel 1 kilometer to cover 1 centimeter of actual space. Same thing for the galaxy. They get scaled based on the scale that their parent node is that they're spawned from in the universe level. And yeah, so that's kind of the secret, is that everything is actually, yikes. Secret is that everything is actually moving at different rates of speed. It's just doing so in a way that makes the perspective convincing. So like when this galaxy spawns in, which it just did, it doesn't spawn in the same location as that particle. It spawns in really far away from that particle because the galaxy is really big, but it's the distance it spawns away is the amount of distance that it takes to make its perceived size be exactly the same size as the particle. And then likewise, as we get closer to it, which something's wrong with my particle material here. It's not fading out correctly, but you get the idea. Everything is in motion. The player's in motion, the universe is in motion, and the galaxy are all in motion, and they all move at different rates, but they're all based on the player's rate of change. So we can actually take a look at what that looks like in, say, our universe actor. In the tick function down here, we invoke this apply parallax offset function. So what we do is we fetch the player's pawn, and we get the player's pawn location as our current frame of reference location. And then down here, we calculate a parallax ratio, which is our speed scale divided by our unit scale. We calculate our player offset, which is our current frame of reference location, minus our last frame of reference location. We update our last frame of reference location. Then we take the player offset and we multiply by 1 minus the parallax ratio. And then we set the actor's location to its current location plus that offset that we just calculated. And what that ends up doing is if we set our unit scale to, like I said, 100,000, then for me, like if I'm moving in the game world, the universe is moving with me. And after I've moved 100,000 units in the game world, relative to me, the universe will have moved 1 centimeter in the same directional vector as my 100,000 offset from wherever I started. And that's how that works. So that's kind of really important concept here. And what this lets us do is arbitrarily control our warp speed and let us make this appear to be very large while still maintaining some level of precision without having to actually make it trillions of miles. It doesn't have to be that big. We can just change our speed factor and it will feel slower. We can change our unit scale and it will feel bigger. So the next thing we do, there was a bunch of research I did. We have this point cloud generator class, and we'll look at the header here because we have 2 major generators right now that are important. We have our base. We have our Galaxy Param struct and Galaxy Param factory. This is what handles our proceduralization. It's also the biggest method in the whole thing is the constructor for the param factory, but it's just setting a bunch of parameters basically. Then we have our Galaxy generator. This is a point cloud generator, and what it basically does is populates an array of generated data that we can then inject into our octree. And we have some other things like these are size probabilities for stars based on some astrophysics that I pulled up. It's just like when you insert into the octree, every shallower depth you insert into, you can effectively think as being twice as large as the next depth under it. So wherever our smallest stars are, we generate the most of them, and then this would be the chance to be twice as big as our smallest, 4 times as big, 8 times as big, 16 times as big, 32 times as big, 64 times as big. So we represent stars from our smallest to 64 times bigger than our smallest with this range. And these are just probabilities of those things spawning. And then we have a stage generation where we have a series of helper methods that we invoke in sequence to basically generate the galaxy point cloud. I'm not going to go super in depth on that right now. Just understand that this is doing a lot of async generation. I spent a lot of time optimizing it, trying to make it go as fast as possible, fiddling with the gas accumulation and things like that. And then we also have this universe generator, which is doing the same thing, just at the universe scale, and that's what's generating like our kind of cosmic web structure that I was showing earlier. So, oh, and we use fast noise too. I already used that in my planet project that generates procedural planets. So there's no real reason for me to pursue any other noise libraries when I already have this one integrated. So for example, the universe cosmic web function is actually a fast noise 2 encoded node tree that I use to generate the noise. Another thing that I'll talk about here is the short circuiting of the initialization. So if we take a look at universe actor, or actually galaxy actor is a better example because this one does more things and it has to be more performant. So we take a look at the init method here. Because you're flying through space, you could and because it takes about a second to generate the galaxy in total, you could very easily like zoom past a point, trigger a galaxy spawn, and have exited the area before it's time to actually render the galaxy before you finish generating it. And so basically what we've done is break up our initialization process into stages. The first stage is initialization of data. So the first thing we do is we check our lifecycle state after this is called, just in case, you know, we've already exited the area. When we exit the area, this will get set to pooling. So if we ever hit pooling, we just return out and we skip the rest of our initialization. It saves us a lot of computation. If we're like zooming past lots of points that would all spawn galaxies, now maybe they only have to run 1 or 2 steps each instead of the whole thing. The next thing we do is initialize volumetric. So initialize data, if we take a look, this is pulling out, this is running our generator, our galaxy generator. We run it here. Then we come down here and we run our bulk insert position in our octree, which is a chunked bulk insert, multi-threaded chunked octree bulk insert. I basically make chunks out of the layer that I'm going to use for the volume data, because we need to fetch those exhaustively anyway, so there's no reason to not just use those as our chunks as well. And then each of those chunks gets a set of points that will be inserted into it, and each chunk gets its own thread to handle sequential insertion of those points. So we do our bulk insert. This is going to populate a couple of useful collections of nodes that we have here. It's going to give us our volume nodes, which again, like I said, is that 32 by 32 by 32 array of nodes that we're using for our volumetric effects. And then it generates our point nodes, which this would be our stars. The next thing we're going to do is we have a series of arrays that we use to populate our Niagara particle system. We're going to populate those in a parallel 4, where we basically take each node, we pull out the position, we pull out the scale, and we do our size calculation, which is here. The node's extent times 1 plus the node's density determines our scale. So our scale that we're feeding to Niagara is a diameter. Our extent, our node extent, is more akin to a radius. So we know that each subsequent level you go up the tree, you're doubling in size. So we basically need a way to randomize between the scale that we would be at if we were 1 node deeper, which would be half our size, and the scale we would be at when we hit our maximum size, which would be our diameter, which would be 2 extent. So if we know that the node under us is half our size, then our minimum size would be 1 extent, or a radius, because we're talking about a diameter that we're getting out. So extent would be half of our desired size, and then we allow the density to determine how much of the remaining scale of the node the point will fill up. Next up, we've got colors. This is pulled from our composition value off of our nodes. And then finally, we have this pseudo volume texture equals generate pseudo volume texture from MIP data. This method I'm going to go into in specific because this was a really cool optimization. So when I started this, I was using volume textures, and now I'm using texture 2Ds to represent my volume data. And we're doing it in something called a pseudo volume format, which basically looks like a bunch of slices. I might have one laying around. Let's see. Yeah. So here would be an example of a pseudo volume format. So you basically have like each of these slices will have some resolution, and then you'll have some number of slices on the z-axis to represent the third dimension. So we basically generate one of these on the fly asynchronously. And the whole reason that we switched to using this over using volume textures is because there's this article from Peter Leontov that I found, and this talks about asynchronous creation of textures at runtime in Unreal Engine. Unfortunately, a big very important piece of this is this call. Let me find it here. RHI async create texture 2D. There's no equivalent to this for volume textures, so there's no way to apply this logic if we wanted to use a U volume texture. So we switched to using U texture 2D. We changed our upscaling that we're doing. So if we go here, we have this upscale logic that basically takes in our direct MIP data, our 32 by 32 MIP data, and this will always upscale it to a 256 by 256 by 256 array of volume data. So this upscales that data, and the reason we do that is so that our volume data can be A, smoothed, and B, it will align with the resolution of the noise textures that we're using for distortion, which I will get to here in a moment when we talk about the materials. So this will take, like, the first step is we extract our volume data from the octree, which is actually done by our bulk insert. The nodes it returns are our volume data. The next step is we upscale it, and then the final step is that we call this generate pseudo volume texture from MIP data. This just takes a T array of UN8s that's in a specific expected format for our 256 by 256 by 256 pseudo volume texture, and we have all of this hard coded because it's always going to be the same size. So we create a dummy texture with just a 1x1 size, so it's pretty much instant. This part has to be on the game thread. Next up, we do our async texture creation call. We call this RHI async create texture 2D, which will dispatch a thread, which will basically begin copying our texture data to the graphics card and will return us a reference to that texture data. And then finally, we switch the reference in our texture. Instead of having to do like a full data copy at this step, because this has to happen on the render thread, all we have to do is switch out the reference to point at a different reference. So that's basically what we're doing. So it's basically a pointer swap here. So what we're basically doing is generating a bunch of data asynchronously, generating a texture with no data in it on the game thread, copying, or basically creating a texture reference asynchronously with the data we created, and then finally swapping a pointer out on the render thread to point at a different point in the GPU. The end result is that we can generate our texture at runtime asynchronously with no visible hitches or anything like that. This is the only way I was able to find to do that. Everything else I tried had rendering hitches when it would try to generate the texture. There's just nothing I did aside from this would make it like actually work. So yeah, that covers that piece of it. Chunk bulk insert, if we take a look at our octree, we have bulk insert position. It takes an array of point data, which is the same data structure that our generator uses. It passes out an array of inserted nodes in volume chunks. So the first thing it does is it pre-populates the volume layer exhaustively. So our layer that we're extracting our volume from just gets populated with a bunch of empty nodes. The next thing it does is it divides all of our point data up into baskets for our chunks. So we take our input point data, we split it up per chunk, and we add it to an array there. And then finally, because this is the expensive part, we create a parallel 4 with our number of chunks, which is calculated here, and then we loop inside here to insert all the point data for that chunk, and each one of these is getting its own thread. And then finally, once this is done, we're just ending, and we've already populated our output arrays and things like that, so that once this is done, you have your array of stars, or not stars, I guess galaxies in this case, and you have your array of volume data. So by the time you're done running this, you have everything you need to go ahead and call the async texture generation that we were just looking at. Let's see what else. What else is important in this? I have my notes. Oh, pooled galaxy actor spawn and hide and initialization. So our universe actor and eventually our galaxy actor, when we get into generating star systems, uses a pooled spawning method. So at the start, instead of always generating a new galaxy, if we take a look at, for example, initialize, we invoke this initialize galaxy pool, and all this is doing is basically initializing empty galaxies and putting them in the pool. Here I think let's see what our galaxy pool size is. Okay, so just 5, because you're usually not you usually don't need to load more than one galaxy at a time. Like, they're usually far enough away to where if you're close enough to one for it to render, you're not close enough to any others. It is possible that you could be close enough for 1 or 2 or 3 to happen, but that's why we have a pool, right? And I could change this number to allow more or less to be able to exist simultaneously. And then the other thing that we do is when we spawn, let me find it. Here it is. We have these two methods, spawn galaxy from pool and return galaxy to pool. So these are basically controlling our external spawning that occurs from our querying of the octree. The whole reason that we put this data in an octree is because we can spatially query it efficiently. So that's what allows us to scan our surroundings and pick up the galaxies that are close by, and also the correct screen space to warrant spawning a galaxy. When that happens, we pop a galaxy off our pool. We invoke this reset for spawn method, and then we go ahead and configure all of our galaxy's parameters. We calculate its parallax offset where it should be spawned. We set its actor location to that. We calculate a random axis tilt for the galaxy. We set its axis rotation with that. And then finally, we invoke the initialize method on the galaxy and set it to rendered in the game. And we'll get to and this is basically just kicking off the Brock gen for the galaxy. It's that pool, it's that short-circuiting initialization we were looking at earlier. So this is going to cause it to start generating data and then basically keep going until it finishes and actually displays. And then return galaxy to pool. This was another thing that was tricky, and it took me a while to figure out what the actual problem is. Because I was getting a hitch every time I returned my galaxy to the pool. It would freeze for a second. And it turns out that the reason for that is when we reset this octree to be blanked out, it actually turns out there's a crap load of data in there, and that action takes about a second. And I was doing that in just wherever it was occurring, so it could have been triggered from the game thread or the render thread. So what we actually do is I added a lock. This is resetting lock. So we lock it, we sleep for a second to make sure that any operations that were going on finish, and then we blank the octree by making a new octree shared pointer, and then we unlock it. So this lets us, and we make sure that this occurs on a background thread. This lets us basically allow the background thread to handle the resetting of the octree and the garbage collection and such for that, so it doesn't stall. And then once this is done, we finally return the octree back to the pool. So even if the Octree is in the process of being destroyed, it doesn't actually go back into the pool on the game thread until after it's done fully clearing out its memory. Yeah, so that was important. That was a big hitch. It took forever to figure out why, so I'm pretty happy with that. Let's see, what other topics we got here? Okay, polling. So we basically have two pieces. We have this proximity tracker component, and this performs polling. Every time we get an update here, and this runs on a timer, we get the owner's actor location. So this is a component that's attached to our player, like our player pawn. And then we get the sample location, which is the universe's actor location minus the world. This is essentially our local position within the universe. And then we get the sample coordinate, which is switching it to this F64 int vector, which is what we use for our internal Octree coordinates. And then finally, we make this call to Octree get nodes by screen space. We pass it the sample coordinate, the scan extent, a screen space threshold, a minimum and maximum depth if we want to filter on that, and a type if we want to filter on that. And what this does is it will first reject any nodes that are outside of our scan extent. So you basically set a maximum range that you want nodes to be considered for, and if the node does not overlap this extent, the bounding box composed by this extent, then it will be immediately rejected. And then it does another check to do a rough screen space approximation to figure out how big do we think this should be on screen based on its distance from the camera and its radius. How big should it be on screen? And if it is bigger than this, which this is actually like not like this would be like not in percent, this would be like multiplied by the screen scale. So this is probably like a few pixels, right? Like 5 or 6 pixels. But like we're saying, like basically if we think it would have a bigger radius than like let's just guesstimate and say 4 pixels, then at that point we should spawn our galaxy, which it would get basically added to the nodes that would be spawned, and then this returns that set of Octree nodes. Finally, there's some like debug stuff, and then we have tracking. Like we keep track of our stale galaxies, so for each node in our nearby nodes. So we start off, we create a set of our current spawned galaxy nodes, and then for each node in our nearby nodes that we just picked up, we remove that from our stale galaxy nodes, with the end result being that anything left in the stale galaxy node is due for cleanup. And then if we have a universe actor and we don't have the node, in our spawn galaxy nodes, not our stale galaxy nodes, then we will add the node to our spawn galaxy nodes. These are the ones that are currently tracked and spawned. And we will invoke that spawn galaxy from pool method on our universe. And then likewise, after we're done with that, anything left in our stale galaxy nodes needs to be cleaned up. So we check to make sure we got a universe actor, and then we call return galaxy to pool with the node, and the universe actor will take care of the rest, and then we clean up our own internal state by removing the node from our spawn galaxy nodes. So yeah, that's kind of how that works. What else? What other topics here are important? Okay, volume accumulation on insert. I didn't mention this. Whenever we insert a point into the tree, we give it a data payload, we give it a position where we want to insert the point for, and we give it a depth that we want to insert that point into the tree. When that depth is propagating through the parent nodes to get down to whatever depth we want to insert it into, its gas density gets accumulated in all those nodes. So if I inserted 10 nodes into the root, that root would have the sum of all 10 of those nodes that got inserted gas density. At the same time, we keep track of the maximum gas density of all nodes in that layer. So let's say we're inserting at layer 6 like we mentioned, and it's going to generate a 32 by 32 by 32 grid. Then we would keep track of the maximum node density for all nodes in that layer. And that allows us to then normalize the density across that layer before feeding it to our volume texture. So after that's done, we can go back and we have those volume nodes in hand because we called a bulk insert that populates them for us. We take those nodes, we hand them off to our async texture generation, and that's going to generate us a texture. And then that texture is set on the material on an inverted normal unit cube. So let's look at what that is. Oops. All right. And what this is it is a box, if I can see it somewhere, maybe not. Anyway, it's a 1x1 by, oh, it's got the invisible material in it, so we won't be able to see it, but we can demonstrate the material, we can demonstrate the concept with this. It generates a 1x1x1 box, so it's the same size as our world unit, with inverted normals. So when we look at the box, we don't see the front side of the box, we see the back side of the box. And when we do our volumetric ray marcher, which generates our gas effects for the galaxies, we're basically ray marching from the back wall in reverse back to the camera and doing our ray marching that way. And this lets us do this without having to have like a separate post-process volume for it. We can do our ray marching inside this cube. Our ray marcher is an HLSL driven material. We can see briefly kind of what that looks like. So we'll take, here's the universe's gas. Oh, that's the material instance, sorry. It would be this. So most, like there is some logic out here and a little bit here, but the vast majority of the heavy lifting of this function is in this custom ray marcher. I don't want to go super in depth on this right now, but basically the idea is that it's a ray marcher, it marches through space, it accumulates density. We have some logic in here to basically derive colors from our density values. We do our ray marching loops. Another thing that was big here is like most ray marchers include a light marching step, which makes it substantially more expensive. But you can almost consider like nebula level effects as like self-lighting. Like there's nobody casting a shadow on that nebula, right? It's just lit by the stars that are inside of it. So we completely ditched the light marching loop and we do our ray march in a single pass, which makes it much faster and much more efficient, much friendlier on our frame rate as well. Let's see, what else was on this list of things to go over here? Yeah, we went over this. Oh, and the last piece. We have a Niagara particle system. A few of them, actually. We'll take a look at Galaxy Cloud. And basically, this has a series of user exposed values, which I haven't fully cleaned up yet. But the important thing is that we have a colors array, an extent array, and a position array, and a max extent. These are used to determine where's my spawn? Basically, these are used to drive a spawn burst instantaneous, where these rays are used to populate our set of particles. And that kind of goes back to what we looked at a little bit ago in the generate data method inside Galaxy, where we were populating a series of arrays right here. So we populate these locally and then we use them later. Then we have our initialized volumetric, which gets called, and all this is doing is setting up our unit cube mesh setting up our volume material, setting a bunch of parameters for our volume material, the most important one being this noise, our two noise textures. We have volume texture and noise texture. So we're setting our pseudo volume texture that we populated asynchronously, and then loading a volume noise texture, which is used for distortion, and then a bunch of other parameter values that are used in determining the look and feel of the gas. Finally, we set that on the volumetric component. We set the visibility of the volume component to true, and then we finish our promise here so that we can finish our function. And this is what, after you've generated the data, this is what it takes to basically initialize your volumetric effect. And then finally, we have something kind of similar here where we spawn in our Niagara component. We set its bounds, we set its max extent, we set its translucency sort priority. So this is another thing that's important. Because our galaxy is actually behind our universe, we're disabling default depth sorting for all the materials used, from the particle materials to the volumetrics. None of them use default depth sorting. That allows us to set our sort priority for our galaxy to 1 and our sort priority for our universe to 0, and have the galaxy always render on top of the universe, even when it's like actually physically behind it because of parallax. What else? The other thing, we set our arrays so that our array copies happen asynchronously off the game thread, and then we actually activate our component, our Niagara system, on the game thread and finish our promise here. And I think that's getting pretty close to it. So that covers like the basic ideas of the things that had to work. There was a bunch of other research that I went in here. For instance, I did a bunch of research on different types of galaxies and how to create point clouds to mimic them, on the cosmic web and how to create point clouds to mimic that. But those are more like implementation specific rather than like the framework. They're kind of like the details, right? I did a bunch of work like randomizing different archetypes of galaxies. I did a bunch of optimization work and just like very many polish passes and things like that. What else? Oh, I can talk about, yeah. So I do have some next steps. So I just finished doing the screen space based spawning. Before I was just doing a very like naive distance based spawn check, but that doesn't take into account that a galaxy that the largest galaxy is 64 times bigger than the smallest galaxy. So like you need to load the larger galaxy from further away, but the smaller galaxy you may not need to load until you get closer to it. So that's why we went with a screen space based method. The next thing up on my plate is basically the same way the universe actor spawns galaxy actors. The galaxy actor is going to spawn star system actors, and so we'll be implementing a star system generator that just for now is just going to generate the data only model. So when you get close enough to a star in the galaxy, it will replace that star with a star system actor, and that star system actor will use a similar staged initialization. It will have a number of objects that a number of different object types, the star for the system, the planets for the system, any moons for the planets, just random debris, asteroid belts, and then gas and dust. It'll use a pooled spawning system just like our current implementation does. And finally, in order to get this all the way down to the level of our planet level generators, we have the concept of if you're like traveling at warp speed or not. If you're just traveling within the system, like before we would actually spawn in our assets that you can actually like get out and walk around on, then your universal speed factor would be 0, which means that your perceived night sky and point in the galaxy will never change while you're moving around. It would not be until you decide to leave the solar system that we start ramping the speed factor back up, allowing you to travel in between stars in a galaxy or potentially in between galaxies in the universe. So like that's kind of next is we want to go ahead and generate the solar system data model. We want to get it tuned up, we want to get it performant, and we want to get it spawning in at least a placeholder particle system until we can kind of start mapping it to actual assets. And then after we're done with all that, we're going to want a flight model. I just have a bunch of notes here for things that I was thinking, like scanning modes to be able to identify close by stars or galaxies that you could target for like autopilot type stuff. Our baseline spaceflight model that's just like flying around in like actual space at actual speeds. And then our warp models, which would be flying around in virtual space at different speed factors, allowing us to actually like change places in the universe or in the galaxy. And we're thinking about like interstellar mode, intergalactic mode, basically different speed threshold settings for like how we're gonna do that. And then some like warp gates or something might be nice too, traveling from one galaxy to another in a blink. And for something like that, you could, as long as you know where you're going to, so this would be in the case of like autopiloting, or in the case of like a warp, you can actually preload the destination data. So like if I know I'm going to a galaxy and a star in that galaxy from where I'm at, then I can go ahead and cause that galaxy to get spawned, cause that star system to get spawned, warp the player there. It'll be absolutely seamless, no load screens or anything like that. And then when you come out of warp, you'll be right there in the star system you're warping to. But yeah, that's pretty much a high-level overview of the project as it stands currently. It's been a fun project. A lot of research, a lot of learning went into this. One thing I probably should have clarified is that both the universe and the galaxy get parallax ratios, and their ratios are basically derived. So like the universe is just hard-coded, but then galaxies' parallax ratios are derived based on their own extent, so their relative scale to the scale of the universe, and things like that. So we had to do all that calculation, figure out where do you place it, what should its relative like unit scale be, and things like that. But yeah, I think that's it. Let's just cruise around a little bit in the universe, see a few different galaxies, and then I'll wrap it up. Maybe play some magic. Alright, so we spawn in. We have our cosmic web. Once we get close enough for the screen space to get big enough, it will automatically spawn in the galaxy. And then we go up close to it and we can see what type of galaxy it spawned in. This looks like it's a globular cluster. One thing I really like about this is that your night sky is real. So like, it's not just a skybox. It's like any of these points can be visited and there will be a galaxy there, which is pretty cool, right? Like, it's not fake. There really is something in all these locations. Let's go to this small one and we can kind of demonstrate screen space and its benefits. So like before, when it was distance-based loading, this one would have loaded a long time ago, but it didn't load until we actually got close enough to it for it to occupy a significant proportion of screen space. So that's really super duper useful. It basically saves us load and also allows us, by saving us load, allows us to load things from further away, which is what finally got me to a point where I was satisfied with the range at which this happens at, the substitution happens at. So like it's gonna substitute. Okay, it just did. It just built the, so like it substitutes there, and then by the time it gets to about that big on screen, however big it just was, that big. Once it gets that big on screen, it's gonna disappear. So I also want to put a fade in here so that it's not just like hard cutting out. But for proof of concept, it's not really necessary. I just haven't had time to get around to it yet. But yeah. Oh, and then I guess the distortion that I was talking about. So we set two texture values. One is our actual volume data from our gas accumulation, and the other is just a 3D noise texture selected from a basket of noise textures. And that noise texture is used for distortion, which will camouflage somewhat the voxely nature of our gas. So you can see here, the distortion would be the kind of irregularity, like the kind of, it's kind of squished around and irregularly shaped instead of just being like sort of like a soft cubic structure. And that's due to the 3D texture we use for distortion. And it's also the reason that we upscale our volume data to 256 by 256 by 256, because my noise textures are all 256 by 256 by 256, and it just so happens that having them both overlap the same coordinate space and scale there simplifies our material a lot, and also gets rid of some like very ugly artifacts that would occur if you had like a different resolution for one of the textures than the other one. Well, that's cool. But yeah, next up we'll be basically doing the same thing, but for the galaxy, and making it so that when we get close to a star and it occupies a big enough screen space, it will spawn in a star system over the top of it. So that's kind of like coming up in the near future. And then once that's done, we're going to need to figure out the transition from warp to non-warp. So like what triggers that? How do we do that? And then once that's done, we would take the underlying data model of the star system once we've come out of warp, and use it to spawn our actual like planetary game assets that you could like land a ship on and get out and walk around on. And once that's done, we will basically be able to start out on a planet, hop in a spaceship, blast off into space, fly to a different star, fly to a different galaxy, find a star, find a planet near that star, go land on that planet, get out of our ship and walk around on the surface of the planet, get back in our ship, fly back up into space, and we'll be able to do all of that without ever having like a load screen or any kind of hitches or anything like that. We just like, it just works. You go out, you do stuff, and everything just works. But yeah, I'm pretty happy with how this turned out. I think it's pretty cool. Even if nothing else, it would be an excellent skybox generator. We did enough work on optimization to where the load in of the galaxy is kind of mostly imperceptible now. So like you go to a galaxy, pretty good odds that by the time you get to a point where you would be able to tell what was going on, it's already been subbed out and swapped. So like for example, this guy, yeah, we zoomed up to him, but it was already done loading. Standard disk galaxy. Go over here, find another one. Got another one. Pretty cool. But yeah, so I think that pretty much covers it. I just wanted to give an overview now that it's like at a pretty stable, pretty stable and performant position. Like I said, next up we'll be generating solar systems, and eventually I want to link it up to like my planet generators stuff from the other projects. Um, we'll get all the data model generation and stuff done before I start worrying about that though, because that's going to be a massive effort to like combine these two projects together. Like I'm kind of afraid of doing it because it's going to be like a big pain in the ass. But yeah, so um, I mean, it's pretty much it. Unless you got any questions about it or anything like that, let me know. I'm just cruising around right now, having fun exploring my little procedural universe here. I I always get a kick out of the like parallax demonstration though, like realizing that the galaxy's actually over here and that we're just cruising around inside this space while the galaxy's like way over here is just like kind of neat. And we just hop right back into it. Okay, I came on that one too fast for it to actually load in time. The idea would be though, you would have the player in a spaceship that has a limitation on how fast it can travel. Right now, the way I do it, every time I mouse up, I double my speed factor for all the parallax that's used, which would be the divisor. So like every time I mouse wheel up, I'm doubling how fast I travel, and every time I mouse wheel down, I have it. So like if I mouse wheel up a bunch, we can go really fast, which is probably faster than you would let a player actually travel if they weren't using like a um, controlled warp. Like you might let them travel that fastly if they were using autopilot or if they were using like a warp gate or something like that. But when you're using autopilot or a warp gate, you know where your destination is, so you can preload those assets before you start the warp. And then there's no like load in or anything like that. You just like already loaded and spawned your destination before you start warping at all. And then you can warp there pretty fast without any kind of like pop in or anything like that. But as it stands, this is just like spawning real time based on proximity first and screen space second, which is why they should always spawn at roughly the same perceived size, even if they're smaller. Like this one spawned at a perceived size, and if I find a smaller, where'd it go? If I find a smaller galaxy, like, okay, looking over here, I can see one right here that's very hard to oh, I lost it. No, there it is. It's very hard to see, which means it's a smaller galaxy, but it will still load in when it's the same approximate screen space size, which we're about right now. Okay, it loaded in. And now we're at our smaller galaxy here. It loaded in at around the same, around the point where it's like placeholder sprite was about the same relative size on the screen. And we can go in and explore it. I used seven layers of depth for both of these, based on just like some quick napkin math that lets us encompass about 99.9% of scales that you would expect to see in a real distribution. There's some other astrophysics formulas that go into like the point cloud generators, like I did Hernquist prescription approximation, which deals with like the scale of or the concentration of the central bulge of the galaxy and things like that. Ooh, that's neat. And your night sky at any given point, which, because there's a speed factor driving all of this, let's say we wanted to go to a specific star and spawn in like a star system, and we wanted to like go around in the star system for the star, right? Well, I could, if I mouse wheel down a lot, just reduce my speed to 0, and now I'm moving around in real space, but my night sky isn't moving at all, because it's like basically tied to where I'm at. And that's kind of how it'll work when we spawn our star systems, because those will be in actual world space. So yeah, like I'm holding forward and we are moving, but we're not perceptibly moving through our universe because we reduced our speed scale to such a low number that we're effectively immobile in relationship to all this. But then if I mouse wheel up a bunch, we can start moving again. And by doing that, we can make this thing feel a lot bigger than it actually is. The actual size of these point clouds is about 2 billion. It's a little bit over 2 billion unit radius. It's whatever the power of 2 is, that's right over that. So like again, we'll go get in. Oops, I went too fast. We'll find another one. Yeah, so like that one disappeared before it could quite load in. But again, we need to control the player's speed to not allow that to happen. Got like a gray-purple volumetric effect on this one. And our night sky is just where we're at in our current galaxy and in the universe. You can kind of see the cosmic web in the background, the galaxy contributing some of its colors and volumetrics to the sky, and and yeah, we eject, we see that like, oh, it's actually overlaid and they're actually the same size, which I always thought was kind of freaking cool. But yeah, anyway, I think that's it. Later.